In this video, I'll be talking about the history and the theories of pH. Here's a quick overview of the different people and the different theories that we'll be talking about. We'll talk about Antoine Lavoisier in 1774. In 1884, there's a Swedish chemist Svante Arrhenius that came along. In 1909, Soren Sorensen was working in the lab with pH solutions. In 1923, there was the Bronsted Lowery model, and in 1923, also the American chemist Lewis came up with the shared electron pair model. So in 1774, the French chemist Antoine Lavoisier, who was also considered the father of modern chemistry, he was interested in the role of oxygen in chemistry, and he understood that some of the acids, such as nitric acid, which we have here, and sulfuric acid, had oxygens in them. So he went ahead and said oxygen, from the Greek word oxys, is the acid former, and you can see this is nitric acid with 1 nitrogen, 3 oxygens, and the hydrogen here. And that's what he first started working with here. In 1884, the Swedish chemist Svante Arrhenius came up with the Arrhenius model, where he is talking about increasing hydrogen ions in solution, in aqueous solution. So something like hydrochloric acid, which would break into hydrogen ions and chlorine ions in solution, which this would be considered an Arrhenius acid. Of course, hydrogen ion doesn't actually exist, and it would bond with the water molecule and become a hydronium ion in solution, and that would increase the hydrogen ion concentration. That's considered an acid in the Arrhenius model. And according to this definition of increasing hydroxide ions in solution, we could have something like sodium hydroxide, which would increase the hydroxide ions and be an Arrhenius base. So it breaks into sodium and hydroxide ions in solution and is therefore an Arrhenius base. In 1909, the Danish chemist Soren Sorensen was working in his lab in Carlsberg, and this is the first time we've actually seen pH written down. It was a P and an H. He was working with solutions, and he labeled something with the P and the H as the subscript. Now, the exact origin is unknown. Some possibilities, the Carlsberg lab says that it's the power of hydrogen. We could, it's possible it's the German potens, the French, the Latin, or the Latin potential or quantity of hydrogen in solution. Or it's possible that Sorensen was just labeling his solution with pH, because P could be the solution and Q could be the reference solution. In 1923, the Danish chemist Bronsted and the English chemist Lowery came up with the Bronsted-Lowery definition, and this includes the proton transfer model, that an acid is a proton donor and the base is a proton acceptor. So the proton here when the proton here is hydrogen, this becomes the same acid, whether you're talking about an Arrhenius acid or a Bronsted-Lowery acid. But when we're looking at a proton acceptor, so the proton donor doesn't have to necessarily be the hydroxide ion to create hydroxide ions in solution. We could have something like nitric acid, 3 as a liquid, and water. in solution to give the hydronium ion concentration. Here the base is the acid is the same whether we're talking about Arrhenius or Bronsted Lowery, because we're increasing the hydrogen ions in solution, and that is an aqueous. And then we have here the base is donating the proton, but here the hydronium ion was the water that actually accepted the proton, and so the difference here is that would actually be the Bronsted Lowery base, because in this side of the equation, because we've accepted the proton. And then with the Bronsted Lowery definition, we have a conjugate acid, conjugate base. So there's one more layer here. This is actually the acid, and this is the base, which is kind of funny to think about, but in this equation it is, because the water is the proton acceptor, and then this, the hydronium ion, is actually the conjugate acid. And then we have the conjugate base here. In 1923, American scientist Lewis then came up with a definition of acids and bases based on shared electron pairs forming covalent bonds. If you remember about Lewis and the Lewis dot diagrams showing electrons in different the outer orbitals of a compound, you'll see that he was working frequently with electrons, and so his definition, something that's frequently used for an example, is boron trifluoride. Here we have boron trifluoride. I'll write with the 3 fluorine atoms. It's actually hard to see here, but this is the open shell. So let me start again and rewrite that. Let's help you out here. I'm trying to draw with my pen here and think at the same time. So this is the boron trifluoride, and it's the acid according to Lewis, and you'll see that if we react it with ammonia, if we write it this way, you'll see what happens. Ammonia now in the Lewis dot diagram has the extra electron pair on one side of the ammonia molecule, and so this, because they have the extra electrons to donate, this would be the base, and the acid then is here. It's going to accept these electrons, and then we end up with the covalent bond between the two molecules here, and that's where the electron transfer happened, making these an Lewis acid-base pair. So just a quick review of what we talked about. We were talking about the history and the theories of pH. In 1774, the French chemist Antoine Lavoisier was looking at acids that had oxygen, and that's where he actually came up with the original word acid. And then in 1884, Savante Arrhenius had the model of acids increasing the hydrogen ion concentration, and that's where we get the hydronium ion, and the base is increasing the hydroxide ion concentration in solution. So that's his model, frequently what we look at. In 1909, Sorensen labeled the first solution in the lab, and in 1923 there was the Bronsted Lowery model with a proton transfer. So the Arrhenius and the Bronsted Lowery definition of acid is similar because of the proton or the hydrogen, but the bases could actually be different. And then in 1923, the American chemist Lewis, who is known for the Lewis dot diagrams of electrons in the outer shells, then defined acids and bases based on that electron sharing and creating covalent bonds.